Hello, everyone. Thank you very much for joining us live at DevCon 2020. My name is Bowen Song, and I'm joined by my teammate Fuyao Wang and Yichen Ma to present you a project that is originated from the cloud computing class at Boston University early this spring and evolved during this summer. This is a project that's about distributed database where each of the distributed instances are replicas of one another and are kept in sync via Gaussian protocol. You can envision each of the nodes playing a game of whisper, like the picture here, in order to stay in sync and that they communicate with each other using the least amount of communication necessary using the state-of-the-art set reconciliation protocol. Next slide, please. So for our talk today, we will go through the traditional database and its common problems, the distributed database and how it relates to CAP theory, and our design of database and its architecture. Since this is a recorded session, our live demo is going to go last, and if allowed. And then we will discuss the application and the future work available for our implementation. And now I would like to hand it off to Yichen Ma to start us off with the traditional database and its common problem. Thanks.
Hi, this is Yichen. It's my pleasure to share our work to you guys here. Well, this database are very common in our life. For example, in your cell phone, you need a database to store your contacts, and a bank also needs a database to store its customers' information. We can store any information in the database, but when the amount of data becomes large, for example, for a global company, its customers may be all over the world, a single server may not be able to bear such a large load. Also, a single database may drop because of power off, then the customer can't use the service anymore. And these problems may cause immeasurable losses. But a distributed database can solve these problems well. The definition of this is a database in which data is stored across different physical locations. In this picture, we can see they have three databases located in America, Africa, and Asia. These are the common distributed databases today. TypeDB is compatible with MySQL, and it has strong scalability developed by PingCap, and HBase is an open source non-relational distributed database. And the last one, SCD, from CoreOS, is a lightweight distributed key-value database. Because the database is distributed, there will be communication between different database services, which may cause problems. For example, I have $100 in my bank account, and I made a transfer in Seattle, sending $100 to my friends. And at the same time, I use another IP in Boston to complete another $100 transfer. If two transfer occurs at the same time, the both system in Boston will allow these transfers because both servers will see that there is indeed $100 in my account. I have enough money to make the transfer successful. But in fact, totally I transferred $200 to my friends. So you see something went wrong. For a company like banks, they are sensitive with data. They always want to get the latest data. Otherwise, they may lose a lot of money. Everyone can steal money from bank, just like what I said. So how can we solve this problem? To avoid this situation, the bank wants to know the latest information of my balance, right? Speaking of this, I have to introduce CAP theorem to you guys. Every time when you mention distributed database, you have to talk about CAP. CAP stands for consistency, availability, and partition tolerance. Consistency means that we always get the latest data, no matter which node we read from. If the data cannot be guaranteed to be the latest, the server returns an error instead. In our case, the transfer in Boston will be failed because at that moment, my account is empty and the server will be returned an error. For availability, the server cannot return an error. It must return the data even if it is not the latest version. Partition tolerance means that the system continues to operate despite an arbitrary number of messages being dropped or delayed by the network between nodes. Ideally, Cap are the benefits of distributed database, but we are living in the real world, so in reality, at most we can only achieve 2 points at the same time. For the problem of bank I mentioned before, they want consistency. When client A sends a request to transferring, the system will wait until this commit gets both databases in Seattle and Boston. Then my balance will become 0, which will prevent the invalid transfer in Boston. But during this waiting period, any operation of my account will be locked, which affects the availability of the system. But in some cases, we don't really need consistency. On the contrary, we want the availability. So in our project, we sacrifice consistency to gain availability. And that's the end of my part. The next part will handle to Fuyao.
Okay, hi, I'm Fuyao. So thanks, Yichen. Like he said, our goal is to sacrifice consistency and to achieve availability. And our choice is to use Gaussian protocol. In Gaussian protocol, every node is equal. They don't need a leader to control them. On the contrary, they transfer messages between themselves. And they spread messages periodically and only to their neighbors. As you can see in this gift on the right, they are transmitting messages like a pandemic, just like what we are doing now. We should not do that. Okay, so in this way, we got several advantages. Firstly, our database is decentralized. Nodes don't need to know everything about the cluster. As long as a node is connected to the network, it is able to send data to the whole cluster. And we got scalability. The cluster becomes much easier to scale and can grow naturally. Also, we don't care about a temporary failure of a specific node. The other nodes will work continuously. In addition, we have uniform convergence. The data would be spread from mouse to mouse, just like gossip, and the data transfer speed up could be exponential depending on the topology. So the inconsistency of the cluster will become consistent very soon. Based on this, we name our project as the Gossiper. And what's more, it is conceptually hard to comprehend, but easy to implement. Next slide, please. Okay, here's the way we implement Gaussian protocol. Firstly, our P2P communication. The entire network relies on P2P communication, and we use site reconciliation to efficiently synchronize data between different data sources. As you can see on the top left, two neighbors are synchronizing data. And so for site reconciliation, it takes the union of the two sites, and in the case of collision, it takes the later version of an entry. The collision handler is parallel to the database design and can be adjusted to specific system settings, such as data length, purity, etc., etc. And secondly, we have heartbeats. Heartbeats from a node ensures the nodes are healthy, responsive, and contributing to the network. And it is also used to determine whether it is necessary to reconstruct the network or circumvent a specific node. And thirdly, we have LevelDB and open source key value storage as our bottom level store. So we can store the key value pairs in disk. Neighbor list is used for maintaining an efficient communication between the nodes and the rest of its network for heartbeat checking and dataset reconciliation. And the member structure is used for reconstructing network topology in case any neighboring nodes fail and the network falls to suboptimal state of communication. Next slide, please. For example, in a like I just said, in a ring network topology, if one of the nodes is crushed, the cluster becomes the line. With no doubt that we don't want this, but our member list can recursively get the neighbor's neighbor and connect the node to it. Next slide, please. So talking about site reconciliation, it is an efficient way to synchronize data between nodes, and it is our core tech. It firstly determines the union of two sets and only transfers their symmetric differences. It minimizes the total amount of communication, which means the reduction of communication reduces bandwidth consumptions and the amount of time for data transfer. Like in this example, Alice and Bob both have A, B, and E. So we just need to synchronize the D from Alice and the C from Bob. Next slide, please. There are several synchronization protocols already implemented in our professor from Boston University, Ari Trachtenberg's repo, like CPI Sync, IBLT Sync, Kuko Sync, and FullSync. The library is written in C++, and there is also another Golang version in Bowen's GitHub repo. They are shown on the top. It's really welcome for everyone to import or contribute to them. Okay, and then I'll hand it over to Bowen to talk about the applications.
Thank you, Fuyao. Now that we've learned more about the architecture and design of the Gossiper, let's take a look at some of the top applicable situations that could best benefit from the distributed system, such as this one. Our database is best used for a system that can work with weak consistency and require fast write and read operations to any distributed nodes, and especially for systems that require fast scaling and allow P2P communications. And also that its input is not prone to collision. So one of the top examples we have would be the CDN database. This is the type of system that distributes across different continents and cares very little about the consistency, but rather the data gets to places eventually. Not that long ago, the system synchronization between different instances of the CDN metastore is about 48 hours. And each of the metadata entry is less likely to collide with each other. So our database would be best suitable for such a system. There is also the cluster federation. In this year, we finally have the project called KubeFed to federate a set of Kubernetes clusters together, although it is still under a model that requires a hosting cluster to centralize everything. But as the project grows, I believe that later, hopefully, the federated cluster would need a way to keep their data in sync with each other in a less centralized way. Given the eventual consistency nature requirement from the Kubernetes cluster, the Gossiper would be the best fit for such a federation when evolved into a fully decentralized system. And at last, but not least, there is also the smart grid, which is powered by a bunch of IoT devices connected using ad hoc connection on the different type of network topology spread out in the city or even in the country or different worlds. This kind of devices such as traffic cameras or sensors under some bridge to watch the water levels, they require to send data back to a central place for aggregated processing. To do that, the system would rely on the Gossiper to spread data. Devices in remote places could also use the gossiping protocol to send data to its neighboring device and propagate all the way back to a central place or a central cloud for later processing. In this situation, data is individualized for each device so that they are unlikely to collide with each other, and also that it requires read and write at any node and devices, and the system is most likely to care about eventual consistency instead of a fully consistent system. So, of course, these are just some of the many applications that we want to inspire. This type of database is useful for the age of the cloud and distributed systems, and we want to encourage you for involving such an idea into your future designs. Speaking of future designs. Next slide, please. Thank you. In our work, we would like to investigate the best ways to build a cluster of fully distributed nodes and construct their neighbor and member structure to create a most resilient system under different types of network. We would also like to investigate the network topology impact for the system performance. For example, a ring-type network would result in a node only able to communicate with 2 other nodes in the system, whereas in a mesh type of network, it would interconnect all the nodes in the system. Although the ring type of network would result in a system that takes longer to synchronize the entire network than the mesh topology, but the mesh network will also require much more resources to establish such connection, and it's more likely that they require all the devices to be geographically co-located. Next slide, please. So thank you very much. And like all the project at Red Hat, our source code is open source, and it's available on GitHub at my Gossiper, as listed below there. And if you are interested to play around with some of the examples, they're available, and hopefully the we have written enough documentation so that you can understand everything. There's also the CPI sync library that's written in C++. We mentioned a few times in this talk, and feel free to play around with it. Thank you. Next slide, please. And thanks everyone for listening, and hopefully our live demo would go as planned. We would also like to take this chance to acknowledge Ashton Davis for coaching our presentation. Thank you very much.